When sizing wire for longer runs, especially with inductive loads, accuracy is crucial. A commonly used formula is voltage drop equals 2 times K times L times I divided by circular mils, or VD equals 2 Li divided by Cm. While this formula provides a reasonable approximation for residential applications with shorter wire runs, typically less than 100 feet, and smaller to medium-sized loads, generally up to 10 amps, it becomes less accurate for longer runs or high-powered inductive loads. The most accurate formula to consider is voltage drop equals quantity 2 times K times L times the quantity of I plus 0.6 quantity all divided by Cm. In this formula, Vd represents the voltage drop in volts. The K factor is the resistance factor for the specific wire size and material. L is the length of the wire run in feet. I signifies the current draw of the load in amps. I represents the inductive current in amps. It's important to calculate inductive current I, which is found using the formula inductive current equals quantity power factor times I quantity all divided by 0.8. The power factor, or PF, is typically between 0.7 and 0.9 for inductive loads such as well pumps and motors. For wire runs exceeding 100 feet or when dealing with inductive loads drawing more than 10 amps, employing the more precise formula that incorporates inductive current is highly recommended. Let's illustrate this with an example calculation. Imagine a well pump drawing 12 amps located 200 feet away from the electrical panel. The wire used is number 12 American wire gauge, or AUG, copper, which has a K value of 10.2. We'll assume a power factor of 0.8. First, we'll calculate the voltage drop using the simplified formula Vd equals 2 Li divided by Cm. The voltage drop equals quantity 2 times 10.2 times 200 times 12 quantity all divided by 1000, which equals 48.96 volts. Now, let's use the more accurate formula. First, we calculate the inductive current, or IC. IC equals quantity 0.8 times 12 quantity all divided by 0.8, which equals 12 amps. Next, we find the voltage drop using the more accurate formula Vd equals quantity 2 times 10.2 times 200 times quantity 12 plus 0.6 quantity all divided by 1000, which equals 61.44 volts. As demonstrated, the more accurate formula yields a higher voltage drop of 61.44 volts compared to the 48.96 volts calculated using the Vd equals 2 Li divided by Cm formula. This difference arises because the more accurate formula considers the inductive current, which significantly impacts the voltage drop along the wire run. Always consult local electrical codes and regulations for specific requirements and safe practices.